Our focus for this video is multiplying and adding radicals. We will use the product property of radicals to multiply two radical expressions and then simplify when possible. We will also be looking at adding and subtracting radical expressions, but we can only do so if the radicals are like radicals. It's very similar to thinking about having like terms. So like radicals means that the radicands must be the same, so the bases must be the same, and the indices must be the same. The roots must be the same. We are going to assume that all variables are going to represent positive real numbers, and by doing so, we will not have to insert absolute value bars around the simplified form of the nth root of a to the nth power when n is even. So this is going to make our lives so much easier. We're just going to assume that all of our variables are positive. So for our first example, we're going to be looking at multiplying single term radicals, such as the square root of 10 times the square root of 15. I first want you to take a moment and recognize the square root of 10 in and of itself does not simplify. The square root of 15 also does not simplify. But when we apply the product property, this gives us the square root of 10 times 15. And when multiplying, we now have the square root of 150. Now, 150 is also not a square root, but take a few moments and think about what it contains and work backwards. 10 is not prime. 10 contains factors of 2 and 5. 15 is also not prime. It contains factors of 3 and 5. Now, because this is a square root, I'm interested in looking at all of my factors and seeing if anything occurs twice. And notice a 5 occurs twice, which means 150 is made up of 5 times 5 times 3 times 3. And 5 times 5 is 25. It's a perfect square. And then 2 times 3 is 6. It is not a perfect square. So this is equal to the square root of 25 times 6. And now, undoing our product property, we can take the square root of 25, which is 5, and the square root of 6 cannot be simplified. For our next example, we have a lot going on here. We have the cubed root of x squared times y times z squared, and then this is all times the cubed root of x, y squared, z squared. So what we're going to do is group everything that is similar to each other together. So this is the cubed root of x squared, but because multiplication is commutative, I can bring this with the x from the other radical, times y from the first radical, which I can bring with y squared from the second radical. And then we have z squared from both the first radical and the second radical. And so these are all connected through multiplication. So this now gives us the cubed root of, and we're going to multiply to bring these together, x squared times x to the first is x cubed. Y times y squared is y cubed. And z squared times z squared is z to the fourth. The cubed root of x cubed is just x. The cubed root of y cubed is just y. And the cubed root of z to the fourth does not simplify perfectly. But remember, 4 contains a 3. So another way to think about this, the root of 3 goes into the power of 4 once. So we can take az out. And we have a remaining factor of z left under our cubed root. Another way to process this, the cubed root of z to the fourth is equal to the cubed root of z cubed with 1 extra factor of z. Question: simplify the cubed root of 3 times the cubed root of 9. Next question, simplify the square root of 8 times the square root of 12. And your third question, simplify the fourth root of x cubed times the fourth root of x squared. We're now going to focus on adding and subtracting radicals. Now, remember, in order to do so, our radicals must be like radicals, meaning they have the same radicand and they have the same indices. So if we look at our first example, we have 5 times the cubed root of 2t plus 3 times the cubed root of 2t minus 2 times the cubed root of 2t. Notice our radicals are all like each other. Therefore, we simply combine our coefficients. So this is more of a mental step. Because all of the radicals are like each other, we can take the 5 and add it with the 3 and subtract it with the 2 because they are all being multiplied by the cubed root of 2t. So our final answer here, well, 5 plus 3 is 8, and 8 minus 2 is 6. So we have 6 times the cubed root of 2t, which is simplified. For our next example, we need to notice that right now, these radicals are not like each other, but could one or both of them possibly be simplified so that they are then like each other, and then could we combine them through addition? So looking at our first radical, notice that we have the square root of 4, and 4 is a perfect square, so we can simplify the square root of 4. Now s is being raised to the first power, and the square root of s, there's nothing I can do with that. Lastly, for this radical, we have the square root of t squared. Remember from the beginning of this video, we said we're going to let all of our variables be positive. So I do not need to worry about absolute value symbols here. And the square root of t squared can be simplified. And then for our second radical, this is already simplified. There's nothing I can do here. So tackling this first radical, another thing that we need to recognize is there is implied multiplication right here. This is 5 times the square root of 4st squared. So when we simplify the square root of 4 to be 2, that means we have 5, and when we bring that 2 out, it is going to be multiplied by the 5. s, there's nothing I can do with it. But the square root of t squared, because our implied root there is 2, the root and the power will cancel, and leaving us with t. So the only thing left underneath our radical is that square root, or is the s, pardon me. There's nothing I can do with 3t times the square root of s. Performing the multiplication, we have 10t times the square root of s plus 3t times the square root of s. And now our radicals are like each other. And notice also that the coefficients are like each other. 10t is like 3t. So we add the numeric coefficients, giving us 13t times the square root of s. Our next example, we have 3 times the 4th root of 2. There's nothing I can do with 2. 2 is a prime number. It does not break down. But then we have also the 4th root of x to the 5th. And x to the 5th actually contains 4 factors of x and 1 that is extra. So 2 times x to the 4th with 1 extra factor of x, minus the 4th root of, now 32 is not prime. So if we start tearing this apart, it is equal to 8 and 4. 8 is equal to 4 and 2. 4 is equal to 2 times 2. Again, 4 is equal to 2 times 2. Now remember, we're looking at 4th root, so we're looking to find 4 things that are exactly the same. We have 1, 2, 3, 4 2's, and an extra 2. And remember, 2 to the 4th is 16, so 32 is 16 times that extra factor of 2. And we still have an x there. So now we can simplify. The 4th root of x to the 4th is x, so we can bring this x out front. And then what's left underneath my radical is the 2 and the extra x, minus the 4th root of 16 is 2, and we have the 4th root of 2x left over. Now notice that our radicals are like each other. We have the 4th root of 2x and the 4th root of 2x. But what's interesting about this problem is our coefficients are not like each other. So we're trying to perform the subtraction, but we're kind of stuck. But the next move that we can make is we can say that this is equivalent to 3x minus 2, and both are being multiplied by the 4th root of 2x. And that is the end of that problem. Question number 4, simplify. 7 times the cubed root of 3 times x squared minus 5 times the cubed root of 3 times x squared. In question 5, simplify the square root of 75 times d to the 4th plus d times 27 times d squared.